To Ramsey Auditorium at Fermilab. Before we start, please note the following. Standing in the aisles and sitting on the stairs or in front of the exit doors is not permitted. In the event of fire, leave the building using the nearest exit. Exits are located in the front left and front right corners of the auditorium, on the left and right sides of the stage, and at the back of the auditorium through the three main doors. In the case of tornado warning or other emergencies, you will be provided with voice instructions as to the actions to be taken. Smoking is prohibited in this building and within 20 feet of the entrances. Washrooms are located on the opposite side of the lobby, through the doors in the left and right corners.
Good evening. Everybody ready for the first physics slam? Here we go. Okay, so everybody remembers, I'm the guy that's supposed to be rude. So the first thing I'm supposed to do is remind you, if you have a cell phone, a laptop, a pager, I don't know why you'd have a pager, but anything that's going to embarrass you and your spouse during this show, please take a second and turn it off now. So then I'd like to tell you about some upcoming shows we've got. On December the 8th, Saturday, December the 8th, we've got our Christmas show. 3 wonderful Canadian singers, the Good Lovelies, Under the Mistletoe. And then on January the 8th, Dr. Todd Kukin is going to speak on building bionics, about a neural machine interface. It's going to be a great, great lecture. Okay, so without further ado, the first Fermilab Physics Slam, let's welcome COD's Chris Miller.
Whew. Thank you for the sign. That's what I'm talking about. I gotta go home. Thank you. My name is Chris Miller, and I am a professor of speech communication at College of DuPage. I like to refer to it as the College of DuPage, like the Ohio State University. I feel like it gives it more prestige. It was interesting. I was backstage, and I was wondering, why did I get asked? Well, they kept asking me, how did I get looped into doing this physics slam? And I don't know. I don't know why I'm here. I don't understand physics. I know that it starts with a P. That's what I know. But I am honored to be the first, and perhaps maybe the only, but maybe forever, the host of our Fermilab Physics Slam. I'm hoping that in 20 years, yeah, give it up for this. You know, this morning, Dr. Carter was saying this is the first time that he can remember in his 1,000 years of doing this. I don't know he's that old, but let's just say that he is. This is the first time he can ever remember that we are sold out before 1 o'clock this afternoon, which tells you something about how exciting this particular event is going to be. I'm hoping this isn't going to be the first time that we do this. You know, I'm hoping that 20 years from now, I'm going, welcome to the 20th anniversary, in some kind of, you know, I don't even know, some voice that I don't have. I haven't worked on it yet. But the point is this. You're here right now, and you're learning. We're doing a physics slam. Now, why am I here? I am also the co-director of forensics, which is not dead bodies, by the way. Okay, it is a speech team at College of DuPage. So we do prose interpretation and poetry interpretation, dramatic interpretation, and other kind of speeches. And I'm a speech teacher, so I've helped some of these 5 brilliant people backstage work on their presentations tonight. And I guess that's why I'm here to do this. But primarily, I'm here because I'm good at setting ground rules. So I'm here to kind of set the ground rules. Some things I want you to know about tonight. Each one of these incredibly brilliant people that you're about to see is only going to be allowed 12 minutes to talk about their research, what is interesting to them, what they do here at Fermilab, to teach you about physics. I've watched them twice now. I've come out here 3 times, sat right in that particular area, and watched them talk about physics things. And I think I've learned. I think I'm smarter today, but I actually am smarter. They're going to be teaching you about what's going on in terms of physics. And you know, before I even go on, I want to say how cool it is that you're here learning about science on a Friday night. Before I move on, are there young people here? Like you're young? Stand up! If you're young, stand up! I mean, take that in. I mean, you're here tonight, young people, you're learning about science. You know, tell your teachers, yeah, that's fine. Then that's awesome. Your parents, you might blame them, but that's fantastic. But look, young people, that's fantastic that you're here learning about science tonight. I know what I was doing when I was, I don't know, your age. Maybe I was playing, I don't know, Super Mario Brothers. I don't know what I was doing, but I wasn't learning about science. But you're learning about science tonight, and that's fantastic. So tonight, that's what we're going to do. Each one of these physicists backstage gets 12 minutes to talk about physics and to teach you about physics. Now, if by chance, Dave, get ready, if they go over 12 minutes, okay, they get to the 12-minute mark, they're not allowed to go on, okay? One thing I've learned about physicists, or not physicists, but, well, let's just say, yes, about scientists, is that I feel that they're liars. Because when I was in high school, I used to think this about them. Like, I had some friends that went into physics when I was in high school, and I would say, hey, you want to go out on a Friday night? And they would be like, no, I got to stay home and do physics. And I was like, okay, do physics, right? And they would never tell me what they were doing. When I watched these people do their presentations this week, I thought, you're not just doing science, but you're like saving the world. You know, that's what you're doing. You know, they lied to me. I thought they were Clark Kent, right? But actually they're Superman. I'm like the male version of Lois Lane. I'm completely confused by what people actually in science do. I mean, as a speech teacher, I help you work on eye contact and facial expressions and how to wear a suit, sweetly, if I might add. But thank you, and that is true. I do wear a nice, I got to suck my gut in, but that's not the point. But people in physics, they save the world, and there's some things that I'm watching today, and I've watched over the past week, that I thought, thank you for being incredibly smart, and thank you for trying to make this world a better place, and that's what they actually do. So again, young people, thank you for being here. Go into science. I don't know if it's going to make you rich. I highly doubt it, but the truth of the matter is I'll call you Superman one day, and that's a pretty good compliment. So here's the thing. At the end of their 12 minutes, if they get to 12 minutes, okay, listen to this real quickly. If they get to 12 minutes and they go over it, that means they're cheating. And we're not going to let them cheat. So you're going to hear this sound. That's what they're going to hear. And it's incredibly annoying. Now, this man here can't wait to play the sound. He's hoping, he's praying that somebody goes over. He might even just let it go over so the sound goes off. But they're not allowed to go over 12 minutes, okay? When they're over at 12 minutes, you can applaud them, etc. When we're done with all of our presentations, I'm going to bring all 5 of them out here. And then by show of applause, not by, you know, if you've ever been to a poetry slam, you know that we win poetry slams by snapping our fingers. We're not going to snap our fingers. They are scientists, and they need the applause. Okay, they don't have the high, and they're like, I'm not sure I'm so good, but they're good. So we're going to applaud them and cheer and stomp our feet and whistle and get excited for what they're actually doing. But don't do that after they're done. I mean, you can applaud, and that was fantastic. But when we're finished with the whole thing, I'm going to bring all 5 out. I'm going to reintroduce them to you, and then by your show of applause. And it's really just by what you like. Not by how much you understand. Well, maybe understand. I don't know. I'm gonna whatever. But honestly, what you think is what you just like the most, and then you applaud, and then we're gonna at the end of that we're gonna give them an award, which is really just a piece of paper. It doesn't matter. They all have PhDs. They're doctors. They don't really care. They know they're winners. They're smarter than, well, me, of course. But so they don't. But the point is that they're here to give you research. So, like I said, at the end of this whole thing, we'll get them out here. We'll applaud them, and then we'll also have a question and answer. So if you do have some questions that you want answered, that's how questions and answers work. Then we'll have some microphones here at the edge of the stages, and you can come down and you can ask any of the 5 of them some question and answers. They'll go for about 15 minutes, and then we'll go about our business on our Friday night. Is that all understood? Is there any questions that you want to ask me? Fantastic. Well, ladies and gentlemen, let's get ourselves started with our very first speaker of the evening. I have to write them down on pieces of paper because I can't remember what they're saying. Okay, so our first presentation is the Accelerator-Driven Systems by our first Dr. Stuart Henderson.
Wow, physics fans, we don't see this every day here, so this is great. So I'm going to explain a really, really big idea that has the potential to revolutionize nuclear power and nuclear energy by using particle accelerators to make nuclear energy safer and cleaner. So what are those particle accelerators? What do they do anyway? Well, accelerators are little machines, in this case, sometimes very large machines, that accelerate beams of electrons, protons, or ions to very high energy. The first accelerators, built around 1930, could fit in the palm of your hand, and they were able to accelerate beams of protons and ions up to energies of a few 100,000 volts. It wasn't that long ago that everyone had a small little particle accelerator in their living room in the form of a television picture tube. This image is formed by accelerating a beam of electrons to about 20,000 volts and scanning that beam across a phosphor surface to create an image. Well, over time, accelerators got bigger and bigger and bigger as scientists tried to discover heavier and heavier and heavier subatomic particles. So you might look at one of these things and think, wow, that's a really complex, giant machine that produces a lot of science. How on earth does it work? Well, I want to demystify the complexity of particle accelerators with the help of this simple graphic. So follow along with me over here, but this is how a giant big science machine works. So first of all, the scientists locate the on-off switch and set it to on. It's very important. Having set the big switch to on, then some parts start moving slowly, then more rapidly, and then some science happens. And when that science is happening, you can tell it's happening because there are a lot of lights and lightning bolts and flashes. And then the science is over. So now that you know how they work, what on earth do we do with these things? So here at Fermilab, we have large particle accelerators that we use to try and discover and understand the basic building blocks of matter. At our sister lab down the road at Argonne National Lab, they use particle accelerators to try and understand proteins and biological materials. Particle accelerators are used every day to cure cancer, to cure rubber, to make tires, to manufacture plastics, even to inspect cargo, looking for illicit materials. And in fact, accelerators, believe it or not, will play a role in your Thanksgiving dinner because the packaging around your Thanksgiving turkey was actually treated by an electron beam generated from a particle accelerator. So, I know what you're thinking now. Stuart, accelerators are amazing. They do incredible things for society. But what on earth does that have to do with nuclear energy? So I'd like to introduce you to one of the foremost nuclear energy experts in the United States, and I'm going to use that expert to try and explain some of the complicated aspects of nuclear reactors. And of course, that's Homer Simpson. So Homer works in the Springfield nuclear plant, and he's going to give us a quick tour of the nuclear plant so we can understand how it works, and that's going to explain why we need to bring particle accelerators into the act. So it all starts out with the reactor core. The reactor core is where all the action is. So we load the reactor core with uranium fuel. Uranium's an amazing material because it has one particular isotope that if you bombard that nucleus with neutrons, it breaks up into smaller nuclei. It produces energy and more neutrons. Those neutrons then go on to break up more uranium nuclei, releasing more energy and more neutrons. And in fact, this process proceeds in a controlled way to generate energy and then generate power. And of course, reactors are designed and controlled so that the number of neutrons stays constant over time, so that the rate of power production is constant over time. That core is very hot. It generates steam. Steam then turns a turbine. There's cool water that's brought in to condense this steam, and that water goes up the stack as water vapor. This turbine turns a generator. Of course, the generator generates electricity, and then, of course, electricity drives our economy. So, what do we do with the fuel? Well, this is Homer's idea of nuclear waste management. And, you know, there's some similarities to some aspects. Of course, this is low-level nuclear waste that we're talking about. But the fuel that comes out of a reactor is treated very specially and follows a very particular and safe process. So, fuel in a reactor is replaced about every 1.5 or 2 years. That fuel that is pulled out is very hot, both thermally and from a radiation standpoint. It is stored in spent nuclear fuel pools, literally pools of water into which the spent nuclear fuel is stacked and stored, and after a few years, that fuel is cool enough to be stored in what's called dry cask storage. Well, the plan all along was to take this fuel, put it in dry cask storage, and eventually store the spent nuclear fuel in a geologic repository called Yucca Mountain. So this project was started. Well, the federal government put the kibosh on Yucca Mountain several years ago. So now there's not a place to store this spent nuclear fuel, and there's not a plan for what to do with it. So what are the problems with this spent fuel that we're trying to solve? Well, it takes about 300,000 years for this fuel to decay to a safe level, to reach the same level of radioactivity as the ore that is mined out of the ground to make fuel. That's a long time, 300,000 years. Even with this election cycle behind us, compared to that, 300,000 years is a really, really long time. Storing it requires great care, and the vexing thing about this is that only a few % of the energy content of that fuel is actually burned up before the fuel is lifted out of the reactor. So this fuel is actually a tremendous resource, although we call it waste and spent fuel. So suppose we burnt up this spent fuel in a specially designed reactor and did two things: got rid of the nuclear waste problem and also generated a tremendous amount of electricity. That's where accelerators come into the picture. So we can use accelerators to drive a very particular type of nuclear reactor known as a subcritical reactor. This is a reactor that can actually burn spent nuclear fuel. It burns the really nasty stuff in spent fuel, all the while making electricity. This is a special reactor because that chain reaction that I talked about a minute ago with uranium undergoing fission, generating neutrons, causing other uranium nuclei to undergo fission and generate more neutrons. In this reactor, that sort of chain reaction is physically impossible to sustain. So we need, in fact, some external source of neutrons to power that reaction. The reactor can't do it on its own the way we can do in a uranium-fueled reactor. So that brings in the accelerator. We need an external source of neutrons to make the reaction go. So we generate that source of neutrons with a high-power proton accelerator. It has about 1 billion volts of beam energy, which sounds like an awfully large amount of energy, but compared to the accelerators we have around here at Fermilab, we would consider such an accelerator a low-energy accelerator. But it does have a tremendous beam power, 10 megawatts of beam power. That's the power carried in the proton beam. That is equivalent to the power needed to supply about 5,000 households with electricity. So it's a tremendous amount of power. But it's fundamentally the same type of accelerator that we use for particle physics. And in fact, my colleague Sheldon Tschirhart in a moment is going to describe Project X, and that's the same sort of accelerator that we need for Project X. So we take that beam, direct it into a nuclear reactor, and it strikes a particular type of production target that's good at making neutrons, a target called a spallation target, coming from the word spall, which means to break up into little bits. So protons strike this target, generate a lot of neutrons. Those neutrons power the fuel in this reactor, which burns waste and generates a lot of electricity. So, why use accelerator-driven subcritical reactors? What are the advantages? Well, the reactor remains subcritical at all times. So that means it's physically incapable of having a Chernobyl-type nuclear accident. The reactor is turned off when the accelerator is turned off. So if there is any detected problem with the whole system, one simply shuts the accelerator off, and then the reactor is in a safe state. And if you know anything about accelerators, they really prefer to be off. Such a system will burn up used nuclear fuel, reducing the nuclear waste storage problem. So in fact, with a sufficient number of these systems, it's possible that we could burn up enough fuel to avoid a Yucca Mountain sort of storage facility. In fact, that spent fuel can be transmuted, is the fancy word we call it, changing some isotopes into isotopes that are easier to deal with, so that it's safe to handle in 300 years rather than 300,000 years. It lets us also use new types of fuels with far fewer side effects that are related to spent fuel. So accelerators are wonderful, marvelous things. They impact our lives. They contribute to our quality of life. And in fact, maybe the next big use of particle accelerators will in fact be to solve the nuclear waste problem and provide cleaner and safer nuclear power for future generations. And at this point, I like to remember the wise words of Homer Simpson, who said, "Trying is the first step towards failure." Thank you.
Thank you, Dr. Henderson. Our second speaker this evening is Dr. Chris Stoughton with Holography of the Universe. Holography. See, I'm talking. That's what I'm saying. I don't know.
Where's the clicker?
Dr. Stoughton, please.
Thank you. A hologram is a wonderful thing. You can fill up a room, a three-dimensional space, with an image that comes just from a two-dimensional surface. Think about that. Everything I need to know to describe that whole volume is contained right here in a flat surface. Scientists have something called the holographic principle, which says that not just the special hologram, but all of reality is described that way. So think about this room. All the information in this room, everything going on in this room, can be painted just on the walls. That's all there is. Think about how much paint it would take to paint the ceiling and the walls and the floor of this room. That's not too much compared to the amount of paint it would take to fill up the room. The holographic principle is kind of strange. Well, how do scientists get these ideas anyway? Right? It came by trying to understand how the two great theoretical accomplishments, quantum mechanics and relativity, both of which are tremendously successful theories, how they come together. This book by George Gamow describes the 30 years that shook physics, about 1900 to 1930, and they were the foundation of these two great theories that really describe physical reality. First of all, quantum mechanics. Small things act as particles or waves. I'm not going to explain that to you because we don't understand it. But we deal with it, right? Simple questions like, where is it and how fast is it going? You're not allowed to ask those questions. Okay? Smaller things have more energy. Sounds kind of backwards. And I'm going to demonstrate that to you now with the experiment that introduced, that's the next one, don't pay attention to him. That's the next experiment we're going to do. When you turn on a light, you're doing the fundamental quantum mechanics experiment. Okay? We have here very faintly, the spotlight is turned down on a dimmer switch. And you can see that the light coming out of it is red. When you turn it up, right? It gets brighter, okay? But also notice it's more blue. Now when you turn it down, when the filament is cold, you have long photons. Red photons are cold. You turn it up, you get shorter photons with more energy. Blue photons are hot. Red is cold, blue is hot. This is why scientists sometimes have a little bit of trouble in the shower. It happened one time. Okay. I will now talk about the most prevalent force of nature. It determines why is the Earth round, where are the planets going, the lives of stars, not the Hollywood stars, but the stars in the sky, and the fate of the entire universe. I have here a real live physics teacher, Mr. Brown, my good friend, and he's going to demonstrate this amazing force out to the side over there. Now, before he does this, I want everyone to be a scientist and predict what will happen. And if you think that question is too easy, then answer this one. How do the potatoes know which way to go? Excellent. It works every time. Gravity. Now, the thing about gravity is that larger things have more energy. This is a 5-pound bag of potatoes. A 10-pound bag of potatoes is bigger, right? So photons go the other way. Potatoes, larger is bigger and more energetic. We can sum this up on this chart here. Small things are down here, big things up there. Low energy things here, high energy things here. You are here. The Earth is bigger, right, and has more energy. The black hole at the center of our galaxy is even bigger and has more energy. Notice that it's right on this line. The laws of physics say nothing exists in reality on this side of the line. Everything has to be to the left. Even bigger things, clusters of galaxies, indeed the entire universe falls on that line. To get from us to the universe, our size, you have to multiply by a billion, billion, billion times. That gets you to the size of the whole universe. Going smaller, you have grains of sand, flu viruses. Does anyone have a flu virus here? I hope not. And here are our photons. Notice the red ones are big and cold. The blue ones, okay. Atoms, protons, and our new best friend, the Higgs boson. Right? So they're all there. Now, to get from us down to the Higgs boson, you've got to divide by a billion times, 2 billions, right? The question is, what the heck's going on down here? It's really small. 4 billions. It's farther to go down to here than it is to go to the whole universe, right? Well, you can't just build something that small to look. It's like looking for a contact lens using Google Earth, right? You got to get closer, right? Now, lucky for us, we have an idea. The uncertainty principle helps us get a handle on what's going on there. Heisenberg uncertainty principle, the normal quantum mechanics, says you can't know the position and momentum of something at the same time. This new uncertainty by Craig Hogan is that you can't know the location of something accurately. Things don't really have a location. Now, the accuracy is 35 zeros in front of 1, so that's small, but we're still going to be able to see it. How will we see the... Oops, maybe. How will we see this effect of the holographic universe? Well, by using the holometer. That's what we're building. We're going to very accurately measure with the laser the position of this mirror. You start with a photon. It goes in and hits the mirror. It's half silvered, so the photon splits into 2, right? Goes out there, hits those mirrors, come back. And then what happens next depends on the exact distances, this away and that away. If they're exactly the same, the photon goes out and no light comes down here. Okay? If there's some uncertainty in those distances, a little more light's going to leak out. So if the universe has this holographic property, and if that causes the uncertainty in this position, we'll see some light here. That's the experiment we're going to do. What does this mean, if it's true? We like to think that position is easy. Where are you? You're sitting right there. But when you look carefully, asking about an exact location might not be a fair question. Indeed, space and time would be emergent. This is a new concept, being emergent. Let me give you a couple examples of that. It's a little bit abstract. You all recognize this famous painting? Well, maybe if I zoom out, it'll be easier for you to recognize the shapes that emerge from those dots. Okay? And another thing I like to think about as an emergent phenomenon is waves. What is a wave? It's just water, but it's a very special kind of thing that's going on with the water. And you know what? This is Fermilab. Let's do an experiment ourselves. If we can have the house lights, please. I would like to create a wave here that will be emergent, right? And if we could start over here, please. You all know how to do the wave? Okay, let's wait. Let's loosen up our arms. Everyone know how to do the wave? We'll start over here and see how far we get. If you want to, right? Okay, are we ready? 1, 2, 3, go! All the way, all the way. Come on, 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 come on. Okay, good. I have a question. I only have 12 minutes. I have a question. Did the wave exist? Where did it go? And even worse, we'll go this way next. Even worse, what's going on in the armrest while you're doing the wave? Okay, you ready? 1, 2, 3, go! And it makes it. Now, since this is Fermilab, we like to collide things. Over there and over here. Are you ready? 1, 2, 3, go! So we've done an experiment, and we're going to do the experiment. You don't have to believe the crazy things I said about holometry, that we're really living in a hologram or something. We're going to do the experiment. And I'm very proud to be working with this group of people at Fermilab to do this. We've been working for a couple years. And if we see any extra light coming out of that thing, we'll let you know. Thank you very much.
Thank you, Dr. Stoughton. Okay, our next presentation is Mr. Dr. Doug Glenzinski, and his presentation is entitled Discovery Science with Muons. I said that correct. Good luck, Dr. Glenzinski.
Hi, good evening. So the title of my talk is Discovery Science with Muons. What I'm actually going to talk to you about is why I love my job. Why is it, after 20 years, I still am excited to come to work each day and do physics? But before we get there, I have to tell you a little bit more about myself. For as long as I can remember, I wanted to be a scientist. In fact, a few years ago, my mom pulled out a worksheet that I had done in first grade, and it reminded me that when I was 6 years old, my favorite color was black. My best friend's name was Todd, and that when I grew up, I wanted to be a scientist. And my excitement of science didn't waver or wane over the decades of school that I endured. In fact, I remember in college, we had an assignment. We had to imagine winning an award, and we had to write an acceptance speech. And my classmates, they imagined winning Tonys, Emmys, Oscars. I imagined winning a Nobel Prize in physics. Now I bring all this up to emphasize the fact that I've dreamt of doing discovery science for a long time. And I've had the pleasure of pursuing it here at Fermilab. And these days I work on an experiment that could potentially reveal a new paradigm of physics. And it's called mu to e. So in the remaining minutes I have, I want to tell you what is mu to e, why is it important, and how does it work. So mu to e is it's an experiment that we're planning here at Fermilab. And if all goes well, we'll begin taking data about 5 or 6 years from now. And the object of this experiment is to look for a very rare decay of a muon. In fact, that's what the name means, muon to electron, mu to e. Now, before I go any further, I should probably tell you what a muon is. It's very much like an electron, except it's 200 times heavier. And we've known about them for a long time. We discovered them about 75 years ago using cosmic rays. Cosmic rays are protons from exploded stars that are constantly raining down on the Earth. And they make muons when they interact with the nucleus in the atmosphere. Now, in the 75 years that we've been studying muons, we've basically only ever observed them to do one of two things. They either interact with the nucleus to produce a neutrino, or they decay to produce an electron and two neutrinos. The mu-to-E experiment is looking for evidence of a third thing. That's a muon interacting with the nucleus to produce an electron. So why is this important? To understand that, I first need to tell you a little bit more about the science that we do at Fermilab. It's a branch of science, and it's called high-energy physics. And us high-energy physicists, we're basically aiming to answer two questions. The first question is, what are the elementary particles? What are the tiniest bits of matter out of which everything else is made? And the second question is, what are the forces that govern their behavior? So we have a pretty good answer. These are the elementary particles. We think there are 12 of them. 6 are called quarks, and the other 6 are called leptons. And the only one of these 12 that I'm sure all of you have heard of is here in the left-hand corner. That's the electron. Next to it is its heavy cousin, the muon. And to understand why we think these are elementary fundamental particles, I need to tell you that if you take a few quarks and you combine them in the right way, you can make a proton or a neutron. And then all of you will remember, if I take some protons and neutrons and I add an electron, I can make an atom. And if I change the number of protons and neutrons and electrons, I can build the periodic table of elements. And if I combine those elements, I can make everything we see: the sun, the stars, the planets, everything around us here on Earth. So those quarks and leptons, they're fundamental particles. The forces that govern their interaction, we think there are 3. Call them the electromagnetic force, the strong force, and the weak force. And we even understand how these particles communicate these forces with one another. It's via the exchange of another set of particles, which we call bosons. So the photons, the gluons, and the W and Z bosons. So the full picture, it looks like this. So here are elementary particles, and we understand that their behavior is governed via the exchange of an additional set of particles, the bosons or the force carriers. And we call this the standard model. Now, this picture may sound fantastic, even farcical to you, but there's an enormous amount of experimental evidence that supports this picture of nature. In fact, hundreds of published results over the last 30 or 40 years all support the standard model. In fact, by my count, there are over 30 Nobel Prizes that have been awarded for work that supports the standard model. So this is great, but there's a catch. None of them are mine. No. No, the catch is we know the standard model is incomplete. In fact, you know the standard model is incomplete, because when I talked about forces a few pages back, I forgot a really important one: gravity. It's pretty fundamental to our being here. But it turns out the standard model doesn't know how to express gravity in a quantum mechanical sense. And quarks and leptons, they obey quantum mechanics. So the standard model doesn't include a description of gravity, and that's a problem. But it gets worse. In the last decade or so, this visible, ordinary matter that surrounds us, that's made of quarks and leptons, we've come to understand it only accounts for 5% of the universe. The other 95% of the stuff, we don't know what it is, and the standard model has no explanation for it. The standard model is incomplete. Now, us high-energy physicists, we're a pretty imaginative bunch. We have lots of ideas of what a more complete theory might look like. We have dozens of hypotheses. We have no idea which one, if any, is correct. And that's where mu-to-E comes in. Because it turns out there are many ways this process can occur, a muon interacting with the nucleus to produce an electron. But none of them are in the standard model. So when a physicist asks me, Doug, why is mu-to-E important? I tell him, because mu-to-E is sensitive to physics beyond the standard model, which in plain English means mu-to-E is important because it can make a major discovery. In particular, by measuring the rate at which this interaction occurs, we can pick out which of these theories is correct. Maybe it's this one, maybe it's that one, or maybe it's something we haven't even thought of yet. It may point us in an entirely new direction. And that's why mu-to-E is important. So how does it work? We need 3 things. First, we need to create a lot of muons. Second thing we need to do is stop them near nuclei so they have a chance to interact with those nuclei. And the third thing we need to do is look for any electrons which are produced on account of that interaction. We're going to make our muons the same way that the cosmic wave protons make muons. And to demonstrate that, I'm going to turn this picture on its side. And I'm going to advertise that we're not going to use cosmic wave protons and atmospheric nuclei. We're going to use protons from the Fermilab Accelerator. And we're going to use a very dense target. It's a piece of tungsten. It's going to be about the size of a pencil. So we want it dense, so we create a lot of muons. And we're not going to let the debris fly willy-nilly all over the place. We're going to use powerful magnets to focus that debris so we can get as many muons as possible. Our apparatus is going to look something like this. It's quite big, it's very sophisticated, and nothing like it has ever been built before. The first magnet is our production magnet. That's where our protons come in and hit our tungsten pencil. And all the debris, that's a magnet, it's going to focus it into this second magnet, this funny-shaped magnet. This transport magnet, its job is to carry the muons that we care about from the production magnet to the stopping target over here. The stopping target is that red cylinder. It's going to be made of aluminum foil. So we want to stop the muons in the aluminum foil so that they have a chance to interact with the aluminum nuclei. The detector magnet houses equipment that's going to very precisely measure the energy and momentum of any electron which emanates from our aluminum foil stopping targets. We're going to smash 6 trillion protons into our tungsten pencil to produce 13 billion stopped muons. We're going to do that every second for 3 years. And by the time we're finished, we will have stopped 1 quintillion muons. That's a billion billion, or a million million million, or 1,000, 1,000, 1,000, 1,000, 1,000. It's a staggeringly large number. In fact, it's been estimated that there are 1 quintillion grains of sand on the Earth's beaches. So why do we need such a big number? Well, it turns out that at most, this rate, it's predicted that rate, the biggest it is about 1 in 1 quadrillion. There's only 15 zeros there. So to be sensitive to such a very small number, you need to start with an enormous number of muons, like a quintillion. So high energy physics, it's at a crossroads. We have this beautiful theory. It describes 30 or 40 years of experimental data, but we know it's incomplete. And we have lots of ideas of what a better theory might look like, but we have no idea which one is the right one. In mu to E, it's designed to discover which direction is the right one. And that may be worthy of a Nobel Prize. Thank you.
All right, our next presentation is a little bit different. So it'll be a dramatic interpretation. Many of you have been to plays, and you've seen well, we've seen plays, I guess is what they call them. So the next presentation is by Dr. Deborah Harris, and this one is entitled The Neutrino Monologues.
Need the Dear radioactive ladies and gentlemen, can you believe this? Energy is missing from the atom. We don't understand it. And so naturally, my superior, Wolfgang Pauli, writes a letter with some crazy idea to explain it all, and then he sends me to read it at this physics conference. As the bearer of these lines, to whom I graciously ask you to listen, will explain to you in more detail, I have hit upon a desperate remedy to save the law of conservation of energy. Mr. Chadwick over in England, you see, examining radioactive decays where so-called beta particles are made, observed that there was less energy at the end of the reaction than there was at the beginning. So Professor Pauli's idea is that there must be some other particle carrying away that energy. But it leaves no trace in the detector, so it must be electrically neutral and not interact too often. But really, if the professor actually believed in this theory, in this desperate remedy, do you think he would just send one of his minions to explain it at a conference? Surely he just doesn't want to face up to Niels Bohr. Dr. Bohr claims that this can all be explained with Heisenberg's uncertainty principle. He says that in quantum mechanical processes, energy is simply not conserved. Professor Pauli's excuse for not being here does not inspire confidence. Unfortunately, I cannot appear in Tübingen personally, since I am indispensable in Zurich because of a ball on the 6th and 7th on the night of December. I've seen the professor dance. Believe me, he is hardly indispensable. But you mark my words, if this is all bunk, the humble messenger will bear the brunt. On the other hand, if the new particle actually turns out to exist, then Professor Powell will become even more famous than he already is, and 100 years from now, no one will even remember the messenger's name. Dear Dr. Fermi, thank you for the submission of your manuscript, Tentative Theory of Beta Rays. We regret to inform you that we cannot publish this in our journal because it contains speculations too remote from reality to be of interest to the reader. Sincerely, Sir Richard Gregory, editor of Nature magazine. No use mincing words here. I understand Enrico Fermi is a brilliant man, but this time he has gone too far. He has this theory where he says in beta decays, a neutron can turn into a proton and emit a beta particle, and then this thing he calls a neutrino, a little neutral thing, simply of no use. I will grant you that the theory in the manuscript does describe the pattern of energies of the beta particles that come out of radioactive decays. But Dr. Fermi has had plenty of time to see those results, so I would hardly call that a prediction. And I will grant you this too, I'm intrigued by the symmetry he proposes. Just as a neutron is like a proton but with its charge removed, so a neutrino would be like a beta particle, otherwise known as an electron, but with its charge removed. Then Dr. Fermi calculates what happens when that radioactive decay goes backwards in time. In that case, a neutrino could come in, hit a neutron, and then produce a proton and an electron. And here is where any intelligent reader would find something else to do. According to Dr. Fermi's calculations, the neutrino is over 1 million times less likely to interact than a proton. How on earth are we going to get millions of neutrinos to do any kind of test of this idea? I tell you, Dr. Fermi has some cheek. He wants Nature, the world's premier scientific journal, no less, to publish a theory about a particle that, on the off chance it does exist, cannot even be measured. I say let him publish his musings in some other journal. He must have a cousin who can arrange for this in Italy. I've taken the elevator down to the mine with Mr. Davis for more than 20 years, and I have to say, I really feel sorry for the man. I know it's tough being a miner, but I would have never guessed that it was just as tough being a chemist. Can you imagine a job where you have to build a swimming pool-sized tank deep underground, fill it with bleach, and then wait for these weird particles from the sun, which he calls neutrinos, to interact? When one of these neutrinos interacts, it's supposed to change a single chlorine atom into an argon atom. And the only way Mr. Davis knows that this happened is that he waits long enough, and then he drains this handful of argon atoms out of this huge swimming pool. I would call him a magician, not a chemist. So anyway, this poor Davis fellow, he designs this amazingly challenging experiment. He sees a bunch of argon atoms and proves that once and for all that, yes, the sun does shine thanks to nuclear energy, since he tells me if it didn't, then there would be no neutrinos to change the chlorine into argon in the first place. Before now, every time people tried to figure out what made the sun shine, they ended up with a prediction that it would only last maybe a few thousand years or a few 100,000 years. But apparently it's been around much longer. Even Darwin had figured that out. It's just that nobody knew how. Mr. Davis's neutrinos solved the problem. You'd think the world would celebrate, right? Break out the champagne. But no, no champagne for Mr. Davis. Instead of calling this a great success because Mr. Davis proved once and for all the sun does send trillions of neutrinos to the Earth every second, everyone is pointing fingers because the number of neutrinos he measured in the swimming pool was 3 times too small. At least so his buddy Mr. Bacall tells me. I've seen how careful Mr. Davis is. He can't be wrong, let alone by a factor of 3. It's Mr. Bacall who must have been wrong. I tried to cheer Mr. Davis up. I told him, hey, Mr. Davis, those neutrinos probably didn't get to your detector because it's been so darn cloudy these days. He keeps laughing at that one for some reason. Apparently, neutrinos pass easily through clouds, or the Earth for that matter, which is why the detector is so deep underground. The ground keeps other particles from turning chlorine into argon. Well, maybe Mr. Davis should just go into something easy instead, you know, like politics. This has to be the strangest job I've ever had in my 20 years working construction. These guys from Fermilab want us to dig a mile-long tunnel with half of it pointing downhill at a 6% gradient and none of it going back uphill. They want this tunnel to make a beam of particles I never even heard of before, neutrinos, and send them to some old iron mine 500 miles away in Minnesota. This job, I tell you, it's been one nightmare after another. This long, straight part, that's where these neutrinos are made. We're digging that out with this tunnel boring machine, just like we're making another subway tunnel. But then once we hit that bad rock, instead of digging out 80, 90 feet of this tunnel a day, we are only getting through 3 feet a day. It's been like that for months. It will never end, I tell you, but you know, everybody keeps chugging down that Red Bull and hoping for the best. They tell me when we're all done digging this big tunnel, they're going to make a beam of these neutrinos that is 100 times more powerful than any other one that's been made. It's funny, they brought all 200 of us on the job into this big auditorium one day. In fact, it kind of looked like this one, but without those handrails. Then this physicist gets up to talk to us. He tells us that they are not just sending these neutrinos through the Earth to Minnesota, but they're going to try and catch a few of them on their way out and see how many they see compared to what they predict from the ones that they see on this side of the Earth. This is going to tell them about how much these neutrinos weigh. You would not believe the history of these particles. First, folks didn't believe they existed. Then, no one thought they could ever actually be seen directly. Then, no one thought they could weigh anything other than exactly 0, even with 30 years of evidence staring them in the face from the sun. Now, because these physicists finally believe the neutrinos weigh something and can change from one kind to another as they fly, we're digging this tunnel. And the experiment that goes in it is supposed to make the world's most precise measurement of exactly how much they do change by measuring these particles after they've flown 500 miles. I don't know what medication these people are on, but it is powerful stuff. So here's the part I really won't believe until I see it. We're only digging this tunnel for the first half mile of that trip. For the other 499 miles, these neutrinos will be going through solid Earth. Here it takes us a full day to go 3 feet, and we're professionals. How can something just zip through without breaking a sweat? When my daughter and I first received this invitation to see an underground laboratory, I was against it. Why should we take a tour in the same gold mine that has killed so many men in my family? I know, I keep hearing it. Mining has gotten a lot safer now than it used to be, but I've always had mixed feelings about this place. My family's been working in this mine for over 100 years. In fact, my grandpa was one of the miners who excavated the cavern for that first experiment. I figured that when my daughter won that Davis Bacall scholarship to go to college, we were done trying to earn our living underground. Why go back now? Of course, my daughter was dying to go on this tour, and if you know my daughter, you know I can't win an argument with her. So we both went on that tour to see what has been done to the mine after the miners left and the scientists took over. Because of this scholarship, my daughter may even work there this summer. It's crazy. I never thought I would see my own child working in a physics lab, but she's practically there. What's next, the White House? After going on this tour, I see that these physicists are not all like those guys on the Big Bang Theory. Obviously, some of them are. But these physicists do view this mind as a sacred place because of its history. It's also sacred because being deep underground makes this experiment possible in the first place. In fact, while we protested the working conditions down in the mine, the physicists protested when folks were threatening to shut down the mine. Although I'm not sure I buy any of this, these physicists say they will do experiments in the mine to tell them if their theory of how the universe came to be is correct. They say that in the very beginning of the universe, there were equal amounts of both matter and what they call antimatter, something that can collide with matter and create pure energy. Yet today, all they see is matter. They can... Oh, come on. I have one more thing. I don't know about this. Given all these crazy stories I heard about neutrinos, I would say you cannot predict anything about what they will do next. What I do know is that thanks to generations of miners who lived and died here, we may find out that neutrinos are the reason we're still here. And my daughter's getting a college education. I don't know what she'll discover with it, but I am sure her kids will know a lot more than we know today.
She had costume changes, so that should... And Dave's all happy, he's all smiles. I got to do my buzzer. There you go, Dave. Our final presentation of the evening is Dr. Bob Tschirhart, and his presentation is entitled Project X. Tschirhart, I think I said that correct, right, Doctor?
You did.
Thank you. See, I heard some... You're on.
Yes. So, oops. One more. Here we go. In her best-selling books, Math Does Not Suck and Hot X, Algebra Exposed, Danica McKellar highlighted the joy of searching for and identifying the unknown in mathematics. Project X is a worldwide initiative led by Fermilab to pursue the unknown in particle physics. So what Project X is, it's the evolution of the existing Fermilab research campus here where you're at, with the recent revolution in accelerator technology based on superconducting systems that we are now putting into place that have been developed by Fermilab and our sister laboratories worldwide. These are the NASCAR stickers of the team members that we hope one day adorn the Project X Accelerator, and we certainly hope one day that we are as successful as the NASCAR and Indy great Danica Patrick. So let's talk about Project Y. Why is Fermilab, a particle physics laboratory, pursuing this new accelerator? And as you heard about from our colleagues, there are some very deep questions in particle physics that we're pursuing, notably the origin of mass, and we had an enormous hint about which direction to go forward from our sister laboratory in CERN, which I'll say a few words about later. The origin of matter, why are there 6 different kinds of quarks, 6 different kinds of leptons? The buzzword for that is flavor. The buzzword for the origin of mass is Higgs, which you've read in the newspaper. And then another very deep question, where did all the matter come from in the first place? And if we believe in the Big Bang, why didn't all the matter and antimatter annihilate and leave us all in a bath of photons? These are the questions that we're pursuing and attacking with Project X at Fermilab. How we do that, the way we do our research at Fermilab is that we have 3 frontiers: the cosmic frontier that Chris has talked about a bit, the energy frontier, and the intensity frontier. And all of these frontiers of research overlay with one another and then interact with each other. I'm going to say a few more words about the energy frontier and the intensity frontier. So the energy frontier exploits Einstein's mass-energy relation. The intensity frontier exploits Heisenberg's uncertainty principle. These are the pillars of modern physics that defines the particle physics world that we live in today. We understand, in fact, describe the properties of particles with mathematical tools called Feynman diagrams that were developed by Richard Feynman, famous and beloved American physicist, and colleagues. So famous, in fact, that he got his face on a postage stamp, and with his Feynman diagrams. This is a 37-cent stamp, so you can tell it was some years ago. So this is, these are two Feynman diagrams to help us understand the energy frontier and the intensity frontier. At the energy frontier, we take particles, matter and antimatter particles, and collide them, make energy, and then make new particles. So at Fermilab, when the Tevatron Collider was operating, we took electrical energy from the power lines, accelerated these particles, and made energy, and then created new particles. That's the tool, that's the technique of the energy frontier. The technique of the intensity frontier is, in fact, to create particles for a very brief amount of time, which is dictated by this equation. Quantum mechanics allows us to create new particles for a very short amount of time, and if we observe enough of them, we can infer their presence. So in the case of the energy frontier, high energy is crucial. In the case of the intensity frontier, high intensity is crucial. This is a picture of particle physics. This is how particle physics works today in the 20th century. Now, how do we understand and think about the uncertainty principle? What does that mean? Suppose that Einstein, instead of developing and changing the world in 1905, decided to become a banker. He wouldn't be thinking these thoughts. He would be thinking these thoughts here. Then this is the governing principle of a banker. I never really understood what bankers did until I actually talked with them. So what do bankers do? Bankers give loans of money, and they'll give you a bigger loan for a smaller amount of time. They'll make a larger investment if they have a sense that the return will be quicker, and they'll give you a smaller loan for a longer period of time. If you would ask your mom for a $5 loan for a year, she'd probably say, yeah, I'll give you a $5 loan for a year. But if you were to ask her for a $100 loan for a year, $1,000, she says, no, that's not going to happen. But if you were to make a pitch to her that I'll be able to cut 10 lawns in one day, and if you give me $100, and I'll give you back $100 at the end of the day, you might say, yeah, I might think about that. So banking, in fact, that are quantum mechanics. Bankers intrinsically understand quantum mechanics, and the relationship between money, the stock market, and arbitrage, in fact, has an interesting relationship between how we do our business here at Fermilab. Now, men in black. If you don't pay the loan back, the men in black show up at your door. In quantum mechanics, the same thing is true, that if the loan of this particle that's borrowed from the vacuum is not paid back in time, then that particle just vanishes. So this is, these guys govern the banking world and the world of quantum mechanics. Our sister laboratory at CERN had a fantastic discovery earlier this year, July 4th. This is a photograph at 10 or 11 o'clock in the morning at an auditorium at our sister laboratory at CERN, similar to this auditorium here. These are the leaders of the experiment looking, I think they think they're in some trouble for discovering the God particle, and they're looking up to seeing what kind of trouble they're in for discovering the God particle. Rolf looks particularly concerned. Fabiola looks at peace and angelic, and Joe looks a little agnostic here. We here at Fermilab, what nerds do at 3 o'clock in the morning, this is at 10 o'clock in the morning in Geneva, Switzerland. This is at 3 or 4 o'clock in the morning in an auditorium that's near here at 1 West. So instead of going to the bars, what Fermilab physicists do is they come at 3 o'clock in the morning to cheer on our colleagues in the discovery of some just fantastic evidence for the Higgs particle. The intensity frontier is different. What we do in the intensity frontier is we make very, very high intensity blowtorch beams of particles, and the more particles that the accelerators produce, the better chance we have of glimpsing a quantum mechanical fluctuation. As Debbie said, one of the tools of the intensity frontier is to shine neutrinos through rock, 500 miles of rock or 800 miles of rock to Leeds, South Dakota. It's an amazing property of neutrinos that we can actually do that. Imagine what you would learn about yourself, or if you woke up one day swapping lives with your mother or your daughter. But think about what you'd learn about the world if you were able to do that. Neutrinos do that on their flight path from Fermilab to these distant laboratories, there's enough time for them to transmute from one to the other, and we learn a tremendous amount in the pattern of transmutation. So imagine what you would learn, and I imagine Lindsay Lohan would probably like to be transmuted into somebody else these days. So, intensity frontier, why are scientists interested in rare events? In fact, as a species, we are fascinated with rare events. It's the human condition. We're fascinated with marriages. They don't happen too much in a normal life. We're fascinated with triplets that you see on the street. Hard to believe these are parents of triplets. They're not nearly exhausted enough. But nevertheless, it's something that's quite fascinating. Rare events can, of course, change the course of history. And let's talk a little bit about the probability of events. What does rare mean? So here are a number of dogs engaged in some risky behaviors, including gambling. So we're going to try to set some scale for rare processes. So just to give you a sense of rare processes. So here are some probabilities. The chance of an American home having at least one container of ice cream in the freezer, 9 chances in 10. I think you'd agree. Odds of being audited by the IRS is 1 chance, 175 to 1. Odds of dating a supermodel are 88,000 to 1. Longer odds in my case. Odds of getting dealt that royal flush are 649,740 to 1. Odds of becoming president, 10 million to 1. Odds of a meteor landing on your house are 182 quadrillion to 1. This is, in fact, about the sensitivity of the experiment that Doug was looking for. The rare process that he was looking for was about 100 quadrillion. So the chance of a muon converting to an electron in the experiment he's pursuing has these kind of odds. That's why we need so many particles to pursue that. So one of the great experiments we're pursuing here, in addition to neutrino physics, is the experiment that Doug had talked about, the search for muons converting into electrons. And that is a process that is, we hope, will tell us something fundamental about our world. Fermilab will study, as Doug mentioned, more muons than all the muons of all the grains of sand on all the world's beaches. So when we study those, we can probe new physics models. These are Feynman diagrams of new physics ideas, where each of these diagrams is a mathematical equation. Now, what's interesting about quantum mechanics, in addition to the uncertainty principle, another thing that freaks people out about quantum mechanics is the idea of superposition. That a given muon is not born to decay to a particular electron. And so all of these processes can democratically interfere. There's not a deterministic fate for a particular muon to decay to an electron. And all of these probabilities exist all at once in quantum mechanics. This sounds kind of weird, but in fact, this idea of quantum superposition is something that's actually very real to us, because we're very tuned in to the idea that young life can grow into many different kinds of possibilities and futures. And particularly in this country, we're supportive and accepting the idea that your fate in life is not determined by which family you're born in, the color of your skin, your gender, that you can make your own destiny. And so this idea of probabilistic futures is something that is, in fact, we know in our heart exists, and it's a strong parallel to quantum mechanics. So this is my last slide. Project X and U. There's a breathtaking worldwide drama unfolding right now on all of these frontiers that I mentioned. With Project X and quantum mechanics at the intensity frontier, we will surely learn something deep about our world. They'll fundamentally change how we think about it and ourselves. And our business at Fermilab is to lead at the frontier of particle physics on behalf of you and this great nation. Thank you.
Okay, well, those are our 5 presentations. So that's part of the show tonight. Now what we've got to do is we've got to elect a winner. So what I'm going to do quickly is we're going to set up our applause-o-meter. And from this applause-o-meter, you're going from your applause, your cheers, your whistles, your stomping of your feet. You're going to help us then decide who is the winner this evening. So what we're going to do right now is we're going to invite all 5 of our presenters this evening up onto stage. I'm going to say their name again, as well as the name of their presentation, and you're going to be allowed 12 seconds. So 1 second per minute that they spoke. In Dr. Harris's case, she might get a 13th second, but that's seems to be fair, in my opinion. So I'll invite all 5 of them out, and what we're going to do is we'll see, Dave will set this up quickly.
Are we supposed to be in order?
We'll get an idea, and we'll see what's going on. So, and after I said once, we'll do some applause, and then whoever has the, let's applaud for them right now while they're here.
Are we supposed to look?
Euro? There we go. Come on, let's go! Woo! 100!
All right, so we're going to practice this one time. So what I'm going to do is I have to pay attention to, Dr. Stoughton, move on this way. I have to pay attention to how many seconds go by.
Uh-oh.
So once 12 seconds goes by, we have to stop immediately because I think it's some sort of scientific thing. We got to go by. I don't know. I was told to do this, so I'm going to do that. So we're going to practice this. So what's going to happen is we're going to plot. I'm going to, try to get you to go. And then as soon as I do this, I want you all to stop. I told them that it's possible that 700 people can stop it simultaneously. That's my experiment. That's a speech teacher's experiment. So let's try it out. So let's try for 5 seconds, okay? Let's applaud for 5 seconds. Here we go, and applaud. Told you it works. Okay, so thank you. I'm going to get my PhD now, too, in applausometer. Physics. All right, let's try this first. Dr. Stuart Henderson, please come to the front. Remember, this is Dr. Stuart Henderson. His presentation was on the accelerator-driven systems. We get 12 seconds. Let's see how loud we can get. Ladies and gentlemen, applaud. Nice work.
Very nice.
Wow.
That's high. That's max 101.3 scientific number. That means loud. All right, Dr. Chris Stoughton. Holography of the universe.
Holography.
I'm more concerned with his name.
Stoughton.
Right, Stoughton. Jesus. Potato Man. 12 seconds. Go. Good work. Good work. 99.9.
That's cool.
Next up, Dr. Doug Glenzinski. Discovery Science with Muons. 12 seconds. And go. Good work.
I like the cowbell.
90. I thought for sure that everyone would get to 100. I never thought this was going to work when we first set this thing up. He's like, I got this whole thing on my iPad. I was like, it's never going to work. Print up 5 pieces of paper. It's working. I can't believe. Okay, next up, Dr. Deborah Harris. The Neutrino Monologues. And go. All right. Our final contestant, our final slammer.
Going to the slammer.
I know, you're slammers now. You can go home and tell people that. I slammed last night. What'd you do? I slammed. Dr. Bob Tschirhart, please.
Sheldon.
Sheldon. It says Bob on here, but I'm going to go Sheldon.
Stuart.
We'll go with his presentation, Project X, and go. One more time for all 5 of them, please. I now pass it on to Pierre. Somebody here? Who did I pass? Oh! Where are you?
Over there.
Okay, I'm sorry. That's you, sir. Come up here. I give you the microphone. That's what my directions say.
I've got something here. Okay, so this was fantastic. I think we are going to celebrate the winner here. I think you saw it in the meter. So let me call Stuart Henderson. But as you saw, this was a really close event. And frankly, although we're rewarding somebody here for being #1 in the meter, he was also the first one, and I think you were fresh.
I think so.
So I'm going to call all the others in recognition of their wonderful job tonight and the great effort that went into showing us all what physics can be like and the excitement that drives us here every day for those of us who are privileged enough to work in a place like this, and the support that we get from you all, our taxpayers. So,
Believe it or not.
Chris. Doug. Debbie. Robert. Sheldon.
Sheldon.
Thank you.
Okay, and we have somebody who did a wonderful job also, Chris Miller.
Yeah!
And none of this would be possible without an audience like you. And so the next applause is for you.
Okay, now we're going to have our Q&A session from the audience.
Okay, so we're in some Q&A. We have microphones with some ushers out there somewhere. Thank you. Sort of a microphone so far in their hand.
It's the wardrobe. Guessing it's, yeah.
Right here, we have one right here. Hands up if you want to ask a question to any of our 5 physicists to ask some questions. So we can start. Want to start here? Yep. Go ahead.
Hello.
Sir.
This goes to the Mewtwo experiment. I guess for another 12 minutes. What will it lead? What ideas of science would change? What are the possibilities that you'll find, and how will it change the theories of science?
Well, it'll just help us clarify which of these new theories might be the correct ones. So some of them that we think about, for example, one is called supersymmetry. So in that case, all of these particles that I showed you have mirror particles that are heavier than theirs. So sort of the number of elementary particles would double. Other theories include additional space-time dimensions that are curled up and very compactified. And so, part of the particle world that we experience is sort of projected into these extra dimensions, which kind of changes your worldview a little bit. Or there are superstring theories, which potentially could unify gravity with the other forces that kind of explain everything as strings, and quarks and leptons are vibrations of those strings. So it would change our worldview quite a bit, depending on which of these things pan out.
Thank you. Let's try it right back here. Sir in the green shirt, go right ahead.
This is for the Mewtwo person. Why couldn't antimatter particles fill in the role of supersymmetric particles in the whole supersymmetry thing?
Yeah, I was worrying about the same thing.
Why is that, Doug?
I was going to say that. I wanted to ask that question.
Good question. Go ahead.
Yeah, what do you think?
Yeah, so I didn't talk about antiparticles. So all of those quarks and leptons that I showed, the 12 of them, they also have antiparticles. So antiparticles are very much like their regular ordinary matter, except they have the opposite electric charge. And in fact, the diagrams that Bob showed are matter and antimatter annihilating into energy, like a photon or something. And what supersymmetric particles do, they all are also partners, except their quantum numbers are a little different. So quantum numbers are adjectives that describe the particles. So particles and antiparticles, they have the same adjectives except the electric charge. Supersymmetric, other quantum adjectives are also different, and you introduce them into the theory to fix certain problems that the theory has. So they play a little bit different role.
Got that? Totally follow. Way over here, sir.
Dr. Henderson, you mentioned that the power of the proton beam going in was 10 megawatt. I'm wondering how this compares to the output power, if you could give an overall efficiency of the process.
Yeah, the much more power is generated by burning up the spent nuclear fuel than the power of the particle beam, and even the power needed to power all the components of the accelerator that then makes the particle beam. So this whole process is a net winner. For instance, with a 15 to 20 megawatt beam of protons, you would be able to generate something like 1 gigawatt of electrical power. So it's a net winner. And it's just from the fact that there's still a tremendous amount of energy, even in spent nuclear fuel, that can be turned into electricity.
Excellent. Another question, right there, please.
I have a question for the winner. In that reaction where you burn up the waste, what are the products or residue, and is it toxic? How do you dispose of it?
So you start out with quite toxic nuclear waste, and waste that sticks around for a long time. Takes many tens of thousands of years for the really bad stuff in nuclear waste to die down. So by transmuting it, you break up those nuclei into radioactive isotopes that are much easier to handle. And it's really a whole bunch of isotopes in the periodic table below those that you're breaking up. But the main point is that they have lifetimes, half-lives that are much, much shorter than the problematic nuclear waste that you started out with. So it still needs to be handled carefully, but maybe only for a couple hundred years rather than a couple 100,000 years.
And I have another question for the winner. What did you win?
I'm pretty sure it's a episode of The Simpsons.
Open it up.
It's a book.
Is it a book? Let's see.
Anyone know the Simpsons theme song?
Wow.
The Physics of Superheroes. Cool.
Hey.
All right. Nice. Cool. That's cool.
Told you they were superheroes.
Yeah.
Where are we at now? Over here? Ma'am, please.
Just curious, if someone per se actually ate the toxic material, how long before they die?
Fortunately, that experiment has never been carried out.
Too bad.
So we don't know.
Where are we at next?
Biology student.
Right.
Over here? Right over there. I got someone down here, too, that's looking for a question.
Dr. Henderson, I'm just wondering if the accelerator version of using that nuclear waste is safer. Why don't we skip the first stage of a more typical reactor? Just skip it and just go right to the accelerator using that nuclear fuel.
Right. There are many schemes for using accelerators and nuclear reactors, and the one I focused on was burning nuclear waste. But there are some schemes using that same sort of technology where different materials could be used as fuel. For instance, the element thorium rather than uranium. And in fact, in some parts of the country, of the world rather, this is quite a focused area of research, trying to develop a whole new fuel cycle based on thorium material rather than uranium, which does what you describe. It skips the first step. It makes nuclear power from fuel that, is just plain old thorium metal that itself is not radioactive and very easy to handle. So there are some schemes that do just what you described.
We already have the waste.
But the reason we focus in this country on the waste is because it's an issue with Yucca Mountain closed and without a geologic repository. Many people are trying to understand what the long-term solution is for waste.
Excellent. Back there in the red shirt.
The nuclear fusion guy. Isn't it 300 years still a long time for it to decompose? And, could we burn it again to shorten that time?
300 years is a very long time, but at least it's a sort of time scale that we can imagine dealing with material as opposed to 300,000 years, which is just very hard to understand what the world would even look like in 300,000 years. So, yes, you're right, it is quite a long time. But it's possible to engineer and design places to store that stuff for a few hundred years.
Excellent. Question right here. We'll take 2 more questions. And just so you know, we'll be having a reception up in the lobby when this is all over, and all 5 of our speakers will be required to go up there. So you can ask them questions up there as well. So we'll take 2 more questions. We'll start right here, and then we'll ask 1 more after that. So
this is for Professor Henderson. Why do we even need that extra stage with the reactor? With the accelerator. Why does the nuclear fuel not combust as much as it could? Why does it only use a tiny fraction of what it could be using in the first part?
Yeah, the nuclear fuel is usually pulled out because the properties of the fuel and the assembly and the materials that encase the fuel reach a point where the assembly no longer has the right sort of nuclear properties that are needed to actually power the reactor. So there's some research going on that has nothing to do with accelerators to try and increase the depth of burn, it's called, into nuclear fuel beyond what we do today. So it has to do with the properties of the material that make up the nuclear fuel.
Okay. Let's take 1 more question over here.
My question is to Dr. Debbie. Where did you find the inspiration for your monologues?
Actually, I didn't get a chance to do 1 paragraph and my thank you slide, but actually those are all based on true stories. There's actually Fermi's letter. So Pauli did write a letter and made some poor guy read it at a conference. We don't know this guy's name. We just know the letter. Fermi's letter, his original article literature was rejected, and it was never published in English. It was published in Italian and German. And there's somebody working at the Sanford Underground Laboratory who told me some stories about, he knew Ray Davis, and he used to ride the elevator with him. Mike Andrews, who worked with the New Me construction project here, told me some of those stories. And then I talked to somebody else at Sanford Underground Lab about tours that they give and the Davis Bacall Scholarship. So it's all based on truth.
There you go. Ladies and gentlemen, one last time for our 5 physicists. I want to thank you for being a part of our first annual Fermilab Physics Slam. We'll be up in the lobby soon. Have a great evening.
Congratulations, man.
All right.
Great. You got him excited. It's a good thing.